So yeah, today or tonight, I'm going to be talking a little bit about what our lab does here at Colorado State University, primarily looking at bird migration and trying to really modernize the way that we use radar data to study migratory birds moving under the cover of darkness. So the use of radar is not necessarily a new tool. It's been around since as early as World War II, the end of World War II. I think the things that we do currently are probably the state of the art in terms of using weather radar for looking at migration, but also forecasting bird migration. Okay, so here's a little bit of an outline of hopefully what we'll cover tonight, and you'll feel quite confident, I guess, in these statements here. So first here, radars can detect critical measures of aerial migratory movements. We'll walk through a number of exercises here, some visuals, and then how we're utilizing these weather radar data. Second point here, I just wanted to take maybe a little bit more of an applied approach. So specifically, artificial light negatively impacts migratory birds. So this is an angle that our lab has focused on for a number of years now, that preceded my even arrival at CSU, at Cornell Lab of Ornithology, and even the University of Oklahoma. So a topic we've been working on for a little bit of time now. And then following that, what are some solutions to that problem? So with this statement here, migratory movements are predictable, allowing conservation action to take place. And what I'll be talking about is maybe a project that some of you are familiar with, the Birdcast project that's in collaboration with the Cornell Lab of Ornithology, CSU, and the University of Massachusetts. I'll try to show you sort of the engine that drives that website and how we apply our science lens to actually creating conservation action. Okay, so I just want to start probably with a visual that's more familiar to most in this chat here than even me. So I just wanted to get you in the mindset here of when are birds migrating, or primarily when are birds migrating, especially the songbirds, and thinking about them moving under the cover of darkness. So this is a photo I took last year, sort of mid-August at Rocky Mountain National Park. And this is sort of the natural setting, right? It doesn't get too much better, in terms of nighttime sky, at least in the lower 48, than probably something along these lines here. So that's obviously not the case of what's happening across much of the US. It's not these star-filled skies at this point. It's, landscapes that are heavily dotted with artificial light. And we'll look at how we go from this landscape to something that's heavily modified and how that's impacting migratory birds. Before we get there, I just want to sort of talk about how we think about birds migrating, how we think about airspace as a potential habitat for migratory birds. So in this schematic, I just wanted to outline some of the mechanisms that's driving birds to migrate at night, some pros, cons of why they would migrate at night as well. So our lab thinks about migration in a little bit different context. So we often, when we study migratory birds historically, would think about a bird migrates and then it stops. And then maybe we go out and we put out a mist net, we band a bird, and then we hopefully track it, down the road a little bit, weeks, maybe months at a different site. But nonetheless, we're still monitoring birds on a terrestrial landscape. Or maybe we do the same thing in an aquatic landscape, for instance. We maybe go out and band waterfowl. But those waterfowl migrate and then they take to the sky. So the actual act of migration happens in the airspace. So our lab, the CSU Aero Ecology Lab, studies these aerial habitats. And this term, or this study, is known as aeroecology. So we focus on birds, but obviously you could apply an aeroecological lens to things like insects or even bats migrating through the airspace. Okay, so some nocturnal advantages. These might be quite familiar to some in the crowd here as well, if not most. So one, obviously, the vast majority of birds that migrate at night tend to be small songbirds. So avoiding predation is obviously one benefit to migrate, or why to migrate at night. Cooler temperatures is going to be another one. So you can imagine, if you've run a 5K or any amount of distance, or just run in general, right? You'd probably rather do it in a cooler temperature. You'd rather be in 70 degrees Fahrenheit versus 90 degrees Fahrenheit. the same is true for these birds. They're flying at high speeds, and they're flying for hours on end, burning up a tremendous amount of their energy, and that heat has to come off as well. So if you can move through a cooler medium, that's going to be quite more efficient. However, the last one here, calmer winds, is likely the strongest driver, at least probably in evolutionary time, of why birds migrate at night. So I'll just show this in this visual here. So as the sun rises, we start to get heating of the surface of the earth. That heat from the sun starts to mix the atmosphere. So winds tend to be stronger as you get further from the surface of the earth. So a number of reasons for that. There's friction close to the surface. That's going to slow winds down. But as that sun starts to heat up the surface, we get mixing as warm air starts to rise. That mixing causes turbulence in the atmosphere. So that turbulence often pulls some of the stronger winds closer to the surface of the earth. If you're a ruby crowned kinglet bouncing through the atmosphere that's quite turbulent, is likely not to be. So if you can move at a period of time when the winds are more favorable, but also calmer, the atmosphere is calmer, you're likely to evolve to migrate during that period of time. And that's what happens as the sun sets. That mixing starts to subside, the atmosphere and the winds become more laminar, and that's when birds take off, moving under the cover of darkness. This is the vast majority of birds through Colorado, but also North America. Most temperate birds primarily migrating at night. So to no surprise here, there's a tremendous amount of diversity of birds that move through the nighttime skies through North America. So this is just a small snippet of birds moving through Colorado area, but we could go on and on just like that. To provide some metrics just in terms of birds moving globally. So around 20% or 19% of birds are considered migratory in some capacity. So those might be long distance migrants, they might be short distance migrants, they might be migrants that move up and down in terms of elevation, but nonetheless migratory by some standard. In North America, that number is quite a bit higher, which is probably not surprising given that we have pretty cool winters. It effectively pushes these birds out of these areas when they might breed there, they get pushed out. So there's generally a lack of food for them. Predominantly they're feeding on insects during the summer. So in North America, we would say, at least for terrestrial birds, we would say around 70% of those bird species are migratory. And then we can divvy this up a little bit further to say, of those 70%, when do they actually migrate? Do they migrate during the day or do they migrate at night? Of the birds that migrate in North America, around 80% of them migrate at night. So those are going to be your warblers, sparrows, thrushes, tanagers, so on and so forth. Birds migrating during the day, probably the obvious ones you would think of, birds of prey, large wing birds that are really reliant on thermal soaring or some sort of soaring through the atmosphere. There's some exceptions there, thinking about things like swallows, for instance, can forage on as they migrate, so they preferentially will migrate during the day. But for the vast majority here, birds are migrating at night, especially songbirds. Okay, so that presents a number of challenges. So it's hard to see these birds. They sometimes fly at high elevations. Sometimes we can hear them through flight calls, but that's a tough technique and tool to really do monitoring at large scales. And when I'm thinking about large scales, I'm thinking about coast to coast across the United States. So this is our tool of choice for studying bird migration at large scales. So this is a Nexrad radar. This photo here is taken at the Wyoming radar, just sort of across the border, at least from Fort Collins. And Nexrad is an acronym here. So it's maybe something that you've heard of. So that just means Next Generation Radar. So these are the radars that if you turned on the Weather Channel, you'd see some data from these more often than not. So you might hear them as weather radars or Nexrad or Doppler radars, all the same technology here. So these radars, this one pictured here and all of them across the US are of this model, WSR-88D. All that means is that this is a weather surveillance radar. It was engineered in 1988, And when it was engineered, it was for the first time, at least on a national scale across the US, had the capability of Doppler measurements. That is, they can measure the inbound and outbound speeds of storms, precipitation, hurricanes, tornadoes, severe weather. We can now see the actual motion of those storms. So in the lower 48, this is where these radars are located. There's 143 of these stations, and they provide pretty comprehensive coverage, from north to south, east to west here. And we get a tremendous amount of data from these radars. So it might be a little hard to see here, but for some sites, we have 20 plus years, nearly 25 years of data now. These data are freely accessible, paid by all of us US taxpayers. Like I said, they're freely accessible. They come in every 5 and 10 minutes. We get new updates, but they're also not just located in the lower 48. So we can go look at data from Puerto Rico, Alaska, South Korea, Hawaii, and Japan and Guam. So generally, allies and territories of the United States have all of these radars on them. Okay, so hopefully you're thinking, great, we now know the technology. What does bird migration actually look like from the depiction of a radar, specifically a Nexrad radar? So this is from a spring night. Looks like I dropped the label here. I believe this is probably mid-April or so. But what we're seeing here, there's a radar, this white dot. There's also one in mainland Florida here as well, but I'm just focusing on the Key West radar here, that white dot. You can see Cuba at the bottom of the screen and then Florida at the top of the screen. And I just want to draw your attention. Some of these things are a little subtle, but the blue wave here, these images and measurements are taken around sunset. So the sun sets, and then you're going to see this burst of birds take off of the islands around Key West, Florida. And then you get this secondary wave, the larger blue-green wave coming off of Cuba. So those are birds taking off at night, moving across the Caribbean Sea here, moving into the airspace of the United States, specifically Key West, Florida, and Florida mainland proper. And then you'll see some weather, precipitation moving up in the sort of moving north, northeast in this image here. So we don't know the species of what's in these data. We suspect it's a mix of, sparrows, maybe warblers, thrushes, tanagers, all the colorful birds that get us excited about spring migration. And it's not a small number of birds that these measurements are coming from too, right? This is likely hundreds of thousands, if not millions of birds coming out of the tropics at this point, specifically Cuba in this case. So again, this is just one snapshot. It's from one radar. We have 143 of these radars. It's from one night. We can now look at thousands of nights just like this. So here we are. We have the lower 48. We have 143 of these radars, and then we get these snapshots. So this is what meteorologists work really hard to show you. So this is going to be your precipitation, right? So in any of the areas that you see some color here, you're likely to see some rain droplets. And this is an image or a data product taken from April 5th, 2019. So again, meteorologists work hard to show you this. What they don't want you seeing is all of this stuff. All of this stuff here is birds taking off around sunset, moving through the airspace of the US. So what we do is the inverse of meteorologists. We work really hard to not show you the weather and show you just the biology. So we now have algorithms that allow us to do this automatically. And this has plagued this field for a long time. This is a hard step that's taken us many years to craft these algorithms to remove that contamination, that precipitation, and then just to be looking at biology. So once we have a clean product, we can start answering really fun and exciting questions. At least I think so. So one question that we might have is, where is the greatest intensity of migration across the US on a spring, let's say an average spring season? So what this image here is the compilation of more than 2 decades of radar data. And what you're seeing here is the cumulative passage of birds through the US. So you can see during spring, the central flyway really lights up. That's the main corridor of birds entering into North America. The intensity is considerably lower through sort of these mountainous corridors as well. There's some bias there, but also it seems like that's probably a real product of just lower intensity. We can say, how many birds come into the US out of the tropics. So we can use these data to make estimates of how many birds are crossing transects. So here, around 2.95 billion birds coming into the US. And then we can see how many birds sort of progress across various transects here. So again, this is the average across many spring seasons. We can do the same exact thing. Let's keep the color scale identical, and let's look at where birds are coming through in fall migration. So we would expect more birds, but if we keep the scales the same, what does this look like? So all things equal here, we can see that there's a lot more yellow on this plot than there was in the spring, denoting that there's more birds migrating. We especially have more birds migrating as they head south in the eastern half of the United States. And we can do that same procedure of how many birds cross various transects. So coming back around 4.24 billion birds, 4.5 across this line, and around 4.3 billion birds going back into the tropics during the fall. And we can start to understand things like what's the net uptick of how many birds were produced, let's say, during the summer and moving into fall migration. So those are some of the tools that we have at our disposal. But I would also just draw your attention that, this is great and we can monitor at this scale, but the reality is that the landscape doesn't look like this devoid black space at night. It looks something like this, an area that's heavily modified by buildings, structures, wind turbines, but also light pollution. So light pollution is quite pervasive, and we're starting to see some of the signs that light pollution is impacting migratory birds. So I'll just start with a case study that we did now probably about a handful of years ago. So we're going to jump to probably one of the areas that you would think as being tremendously photopolluted, that being New York City. So this is Central Park, and as all of us being bird watchers probably know the lore around Central Park during spring and fall migration as being a real magnet for migratory birds. But also we know from what we've discussed that the birds don't arrive in Central Park when it looks like this, but rather looks something like this. A landscape that is surrounded by buildings that are very typically illuminated in some capacity, more or less. One night out of the year, there's even more light pollution than what we're seeing here. And that night is, again, probably something that you're familiar with. This time lapse I took probably 3 or 4 years ago now. And what I'm showing you here is one of the towers of light from the September 11th tribute in light. So this is a tower made up of 44 spotlights. Across 2 towers, there are 88 spotlights that cast up into the skyline of New York City. So you can see these lights from 4 or 5 miles away, or probably much further than that. On a clear night, you can see them as far as 60 miles away, as long as you can sort of see the horizon. They'll go 4 to 5 miles up into the actual airspace. Unless they hit a cloud ceiling, they'll sort of stop and it blocks the light and really diffuses the light. So we have this question of, okay, this is an extreme super stimulus of light on the landscape. What can we say about birds being drawn into at this scale? If we can't detect it here, it's unlikely that light pollution is a dominant issue. So even on a clear night in a photopolluted city, what does a strong light source actually do? So we go out every September 11th and do this monitoring. We go out with volunteers from New York City Audubon, and we just look up into these lights and see how many birds are up in the airspace. So this is a video. The perspective here is I'm laying on my back, looking up, taking a video here, and I'm looking straight up into the middle of one of the towers. So I'll play this video, and you'll see these sort of fuzzy things coming in and out. So all of those fuzzy things here, it looks, just from first perspective, like these are insects. What's going on here is this is about 99% warblers in this image here. There's some diversity that we get coming through here, but all of those specks are made up of things like yellow warblers, northern parula, American redstart, sort of zipping in and out of these lights. Sometimes they're chasing each other, sometimes they're just circling around the lights, and often, you can't hear it from this video, but incessantly giving flight calls as they move through these lights. So all is not lost, though, in this sort of story, right? We now know very convincingly birds are attracted to this light source. But we didn't know visually, it's just hard to count birds coming in and out of those lights. And we needed some objective numbers to say how many birds are drawn into this light and how rapidly are they drawn into the light. And like I said, not all is lost here. So it became very apparent that this was an issue from the onset of when this started in the early 2000s. And what happened is that there was an agreement set with stakeholders here, the folks putting on the memorial and the Audubon, New York City Audubon. So what happens is that when we visually count 1,000 birds, likely a gross underestimate because it's hard to count birds in the lights, if we hit 1,000, the lights would be turned off for at least 20 minutes to allow the birds to clear out. So in this case, in this image here, this is taken September 11th, 2015 at 10:12 p.m. So this is a radar depiction of what's going on over lower Manhattan. The tribute in light is at this black dot here, and you can see it at the southern tip of lower Manhattan here. So in the scale here, red's going to be really the prominent source of migratory birds. So there's some speckling of that here, but again, this is probably just typical active bird migration, around 500 birds surrounding the tribute in light. 20 minutes later, we get a new sample from the radar data, and the lights now have been turned on. So in this image, they're off. This is what it looks like when the lights are turned on. So in just 20 minutes, our estimate is around 15,700 birds surrounding the tribute in light. So it's this near magnetic pole of these birds being pulled off course. And unless those lights go off, this intensity doesn't subside much at all. They just keep circling and circling, causing more risk for those birds and potential collisions with buildings. So over around 7 years of our monitoring here, so 7 years equates to just 7 nights, right? It's only on once a year. We estimated around 1.1 million birds were coming in and out of that light source due to attraction. So it's this tremendous number, but also I just want to keep in mind here that the tribute in light is a unique light feature. It doesn't really generalize to many other things across the US, maybe other than parts of Las Vegas, for instance. What we wanted to do was to create a general understanding of, is New York City just at large the worst photopolluter, or how many birds fly over New York City? So could we actually create a catalog of where the greatest risks for migratory birds would be relative to light pollution? So that's the confluence of light pollution, but also intensity of migration. And you'll just sort of remember back to those maps of where during spring was the greatest activity and where during the fall was the greatest activity. So we start with New York City here, but we scaled up quickly and we started looking at the top 125 largest cities across the United States. It's probably no surprise of why we focus on urban areas or cities, but I'll just really emphasize this point. So in the lower 48, the top 125 largest cities only account for around 2.1% of the total landmass. However, in regard to light pollution, they account for around 35% of all of that light pollution. So it's quite disproportionate of the footprint of the city and then the footprint of the light pollution. Okay, so let's just assume for the sake of time, we did all of that work. We now have a ranking system of how, let's say, how risky it is to fly over a city. We have a list of 125 of those largest cities, and we have it for spring and we have it for fall. So that's what's going to show up in this plot here. There's going to be a spring rank on the y-axis, sort of the up-down axis here. And then on the x-axis, the left to right axis, we're going to have a fall rank. So a city or a dot that'll show up, that would be sort of low light pollution, maybe low number of birds passing, would be in the bottom left. And something on the other extreme, a big city with a lot of light pollution, a lot of birds flying over it, would be in the top right. So this is the way all of these cities shake out here. So I'll just draw your attention to a couple of features. The larger the disk, the larger the city. So those are scaled to the area of the city. And then the color of the dots is scaled to the brightness of that city. sort of a relative color scale here. So the brightest city in the lower 48, probably to no surprise, given what I just mentioned, is Las Vegas. The second brightest city here is New Orleans. And then we can also look at a couple of cities from Colorado. So this is where Denver and Colorado Springs rank here. So Denver ranks 49th during the spring and 54th during the fall. Colorado Springs, obviously a smaller city, all of you know that, 114th on this list and 113th on the list during the fall. The top three cities, I won't show it here, just geographically probably not of terrible interest here, but number 1, 2, and 3 was Chicago, Houston, and Dallas, I think in that order. And it didn't waver regardless of season, spring or fall. Okay, so why should we care about light pollution? So the lights themselves, they don't kill birds outright, right? They don't incinerate their feathers. They don't cause them to combust. It's that they draw them into environments that tend to be risky for migratory birds. So collisions are the thing that we're really concerned with. It pulls them into these urban areas where they have the threat or the possibility of colliding with residences, where we're seeing millions of birds die annually, power lines, wind turbines, communication towers, and buildings in general. So we're losing hundreds of millions of birds due to collisions, and light pollution is this magnifying factor on that. So what can we actually do? What tools do we have at our disposal to try to remedy this situation? To say, maybe there's a strategy here, or maybe there's a night that would be of great importance to turn lights out. So I just want to give you a sense of what migration looks like on a nightly basis across the spring season for, let's say, the Denver area in this case. This is where we have one of our near radars, certainly probably the nearest for Colorado Springs. So the y-axis here just is a relative scale of low to high migration activity, and we're going to go from March to mid-June. So probably to no surprise, we're sort of in this lull right now. Some birds are coming back, but we're not really at the full clip of intense migration just yet. So it starts out low, and then we start to get blips, high activity sort of coming through, pushing into late April, beginning of May, and we're getting our greatest waves of intensity of migration. So this is sort of what each individual night point looks like. On the low end, this is what it looks like on our landscape in Colorado. And at the high end, all of this stuff showing up here as the sun sets is migratory birds. But hopefully you'll see that there's not a ton of nights here that have a tremendous amount of activity. There's some, low-ish nights of activity, but we get the vast majority of the passage on just a few nights. At least in this year, it's just 3 nights. Other years, it might be 8 or 10 nights. It's variable. But if we could say, turn off your lights on these 3 nights, this would be really important. And then these 3 nights, they're not back to back. There's some weather variables that are going to be important here. So these 3 big nights, at least in this season, span 19 nights. Okay, so that's just Denver, the Denver radar for 1 year. What happens when we start to look at how does migration play out across the US? Is it always 3 nights? Is it 10 nights? Is it 20 nights? Where is the vast majority of activity caught up in? So if we rank across all of the stations, 20 plus years of data in the lower 48, we see that just around 6.9% of activity is occurring in the lowest 50% of nights. So there's going to be a lot of nights that the radar's spinning around and it's just not detecting a bunch of birds. We can look at the next 20% of nights in a season. This is, again, spring and fall. We see in the next 20 nights, or 20% of nights, it's just around 10.1% of activity. And hopefully you can see where we're going here. The next 20 nights are accounting for around 28.7% of activity. And then lastly, it's just the top 10% of nights. So basically around 10 nights account for 54.3% of the activity. So hopefully you can see this delicate balance here, right? That if we said turn off your lights from March to mid-June, that might be problematic in terms of getting buy-in. But if we could say turn off your lights on these 10% of nights, 10 nights effectively, that might have some traction. So this is a challenging problem though, right? We need to accurately identify a small portion of nights that are particularly important for bird migration and conservation. So what are our approaches to this? So our approaches here might be, let's use this one as a very basic version. Turn off lights during a period of time. That is a period of peak migration. So in Colorado Springs, peak migration, we might say, for example, Colorado Springs turns off their lights from May 2nd to May 17th. That's the window of time, at least from the radar perspective, that we get peak migration. And we would just say, do that for 2018, do that for 2019, do that for 2025. Just keep doing that year after year. And we would say this is some fixed selection version of this. We're not really dynamic. It's just, that's what happened in the past. That's what we're going to do in the future. An alternative to that is that we turn off lights during specific nights of high activity. So for instance, Colorado Springs, we follow a forecast of alerts. We might turn off our lights April 28th, May 1st, May 3rd, May 4th, May 8th, etc. And we would call this something like dynamic selection. So how do we actually do this dynamic selection? Is it better? Is it worse? Fixed selection sounds kind of easy. Just turn off your lights for the next 2.5 weeks. So when we look at this dynamic selection, again, these are averages across the United States. It takes around 10 nights to capture 50% of migratory birds. That's how I'm going to just play this game here. 50% of birds being quote unquote protected. If we do this fixed selection thing, right, we just say turn off your lights for a fixed period of time. It takes around 19 nights to capture 50% of birds because it's not very efficient, right? We're turning off our lights when maybe some birds aren't migrating. Same is true in the fall or autumn here, around 11 nights. But in the fall, it takes around, if we do this fixed selection thing, this fixed window of time, it takes around 26.5 nights to capture 50% of the migratory birds passing over each area of the US. So that's a little problematic, maybe in terms of that timing. So how, if we wanted to do the optimal thing here, how do we actually create dynamic alerts? What we can do is use radar data. We can use lots of radar data actually, and start to create migration forecasts. So we can link these radar data with predictors of bird migration. So things like air temperature, wind speed, direction, pressure, humidity, longitude, latitude, date, so on and so forth. All of the things that we've learned over the last 50, 60 years of what drives bird migration. So this is just a schematic of how we do this. We link radar data. We call this training data. We learn the associations with those meteorological variables. We create a model. This is a machine learning model. And then once we're confident in that, we just add more meteorology, right? Meteorologists make forecasts all the time of the atmosphere. We use that to convert it into bird migration. And this is what a bird migration forecast looks like. So this is a forecast from April 26th, 2016. The warmer colors being more birds predicted. And in this case, our model does not know what 2016 looks like. We removed all of the data for 2016, and then we made a prediction, and then we can look at what does the radar actually measure. So hopefully you can see the intersection here of where the radar is showing activity and where we predict activity. And then on this night, we predict around 241 million birds taking to the skies on this single night. Hopefully you're thinking, okay, that's great. You got one good case. How can you apply this? How do you actually perform across years and multiple seasons? So this is a study in collaboration with my colleague, Benjamin Van Doren, where we did just that. And we looked at 2017. We held out all of 2017's data, made predictions, compared it against the truth. We explained around 78% of the variance. All that means is that if we explained, if this value R squared was 1, we'd be perfect all the time, slam dunk, every night, night after night after night across the US, perfect forecast. We're never going to get there, but we're not at 0, and we're not even at 0.5, we're at around 0.78. So this is quite good for ecology. We do this year after year. We get really great performance, and it's consistent across years. So we feel very comfortable with our predictions. And then you might say, well, how do those predictions perform into the future? So our best predictions would be if we're predicting migration tonight. But tomorrow we do still pretty well. We explain a little bit less and we have more error. And even if we get out to 7 days in advance, we're still able to, with high confidence, predict the intensity of bird migration. Okay, so I just want to pull back to this figure and I'll sort of go into the home stretch of what we have here. So I'm just bringing back this slide again. Fixed selection, again, 19 nights it takes in the spring to capture 50% of birds, 26.5 nights during the fall to capture 50% of the birds. We know that our forecast model is not perfect. So it's going to have some errors and we're going to make some false predictions of when activity is high. So even after accounting for that error, do we still do better than this fixed selection approach? So this is in practice how many nights we would have to make an alert for to capture 50% of birds. So it's around 13.7 nights in the spring. That's 4 additional nights. So there's some error there. And then in the autumn, again, our error is a little bit higher. We're adding 6 additional nights. So those are sort of 6 maybe false alarms here. But still, this is better than the status quo of what we've had for the last probably 20 plus years of how to do this style of conservation. So still, this is a sort of what we see as an improvement across the board here. So we've now put this into place. I'm just going to show you some examples of what it looks like from peak time of migration, what we're all getting excited about, and then I'll show you where we're currently at. So we have all of these data products now running all the time during spring and fall migration. So this is a forecast for April 28th to 29th, April 29th to 30th, so on and so forth. And you can see how many birds we predict at the US scale. We can see the intensity in these maps here of where there's intense migration and where there's sort of low intensity of migration. We provide all of these things. They're always freely accessible. You can go to birdcast.info or the arrowecolab.com and you'll see this imagery. We've also converted these into alerts. So not just sort of that gradient of intensity, but locally to lower the bar of, is this high or is this not high for my area? We make this alert system of sort of no alert to a low, medium, or high alert status for lights out, or potentially running a wind turbine, for instance. So we can look at Colorado and we can start to see, we also predict how many birds are flying over large cities in our state as well. So again, these things are all accessible and you'll get 3-day forecasts. So this is where we're currently at. So these are our forecasts actually for the next 16 days. So the maps are kind of dark at this point, but probably no surprise to all of you that have been bird watching for a while that we're not quite into peak migration. Some species are returning, but some just aren't here just yet. And we've also have these alerts as well. So these are our current lights out alerts for the next 16 days. So at least one of these maps is for tonight. So not a tremendous amount of activity or even alerts likely on the horizon for the rest of the month. That's when things will start heating up in April. And then I'll just close with my last slide here for our next step. So the next phase of this research is to really start figuring out what's going on in these urban centers. Can we actually use radar data to start quantifying the potential mortality that's occurring at urban centers and thinking about these as potential ecological traps. So maybe a term that you've heard of where light pollution is pulling birds into urban areas. Whatever reason, they're attracted to it and it seems like it's something good for their fitness. The reality is that light pollution is likely driving their fitness down. That is, it's resulting in mortality or the burning of energy. So we're going to start looking at a detailed analysis of light pollution, urban areas through the Great Plains. So basically from Colorado all the way to Illinois, we'll start examining urban areas with a lot of remote sensing data. And this is a project now supported by NASA for the next 3 years. So we're quite excited to get that going in the next couple of months.